Hello, I'm Glyn Atkinson. I'm leading the team of researchers here at Newcastle University working on the Future Electric Machines Manufacturing Hub. We're looking at modular electrical machines and how we can gain the highest power density out of them. Power density is all important in electrical machines, so that means obtaining more power out of a given volume or a given size of machine, or having smaller machines that deliver the same amount of power. The aerospace industry have the Aerospace Technology Institute, and they set a goal of 25 kilowatts per kilogram. So that's a 10 times increase in power density from 2.5 kilowatts per kilogram, or machines that are 10 times smaller than they are now. So that's a difficult challenge for the electrical machine manufacturing industry to meet. There's a machine design equation which can be applied here, and what it says is power is proportional to the volume or size of the machine, the speed of the machine, the magnetic loading of the machine, and the electric loading. These are the areas that we can look at in increasing power density. So we can run the machine faster. The problem there is it requires more specialist bearings. The centrifugal forces are difficult to contain. The other thing we can look at is the type of magnets we use. So we would like to use stronger magnets, but there's no technology on the horizon that is going to achieve this aim within the foreseeable future at least. The other area to look at is the electrical loading of the machine. So we can put more electrical current into the machine. The problem is more electrical current means more heat, and that reduces the lifespan of the machine, in some cases to seconds. So at Newcastle University, we're looking at this aspect of electrical machine design, increasing the electric loading, but managing the thermal aspects of the machine so we can increase the power density. Traditional electrical machine manufacturing uses a needle winding or threading process to feed the electrical conductors into the slots of the machine. The problem is this is more of an art form than a precision engineering process, and we end up with coils which can be a bit imprecise, a little bit inconsistent. It's difficult to predict the thermal performance of an electrical machine. So we're applying a modular approach to electrical machine design here at Newcastle University. By segmenting the machine into separate modules, we can then wind directly onto a single tooth. That means a more precise and more precision wound component with a tighter, denser coil. That means we can put more electrical current into the machine but have a lower temperature rise, therefore getting more power density. We can go further with this modular approach. We can design a machine where the teeth are fully removable. That means that we can make the coils completely separately. We could use pre-wound compressed coils with very good thermal properties, or we could use additive manufacturing using the techniques that our colleagues at Bristol University are working on. These types of coils would have a superior thermal performance. We could put much more electrical current in and thereby get much greater power densities out of our electrical machine. So a modular approach does present challenges to electrical machine manufacturing though. These machines are different, mechanically they're different, thermally they're different, and the assembly of them is different. It's a case of applying this technology where there are advantages for the manufacturer. We're working with colleagues at Sheffield University trying to understand the mechanics of this, seeing how a non-modular machine and a modular machine vibrates differently when it's under test and under operation. We're looking at the electromagnetics of the modular machine, so assessing whether splitting the stator into segments has a magnetic advantage or disadvantage, and we're trying to quantify that for the manufacturing industry. We're starting to do accelerated live testing of modular machines, so vibrating them and measuring the degradation of the machine components over time, visually inspecting that and measuring this magnetically. Another advantage of the modular structure, and we're working with colleagues at Strathclyde on this area, is the disassembly of the machine. The modular machine breaks apart much easier at the end of its life. We can separate the various components, the steel, the copper, and the plastics in there much more easily than in a complete non-modular machine. We're designing a series of 50 kilowatt demonstrator machines designed to an automotive specification to show the different modular concepts we're looking at. Our aim isn't to design the best modular machine for a particular application because there are so many, the specification and the type varies so much. What we want to do is provide real insight, real qualified and quantified data to the manufacturing industry, so then they can decide whether modularity is an advantage or a disadvantage for a particular application. This research will help drive the electrification of transport and the quest for greater power density in electrical machines.